Okay, let's continue for our discussion on section 2.3, the Faraday's law. And here's example 2.4. And in the figure, we have a rectangle grid made of metal wires. And so the three sides are fixed. And the first one, which is plotted as the red bar, is movable. And for this case, it's moving from to the right at a velocity of v sub 0 toward the positive y direction. And as you can see in the figure, it has some background magnetic field labeled as B, and its direction are toward the positive z direction. So it's marked as crosses on the plot. And the movable bar and the rectangular grid make a loop. So as the bar is moving from left to right, and because the magnetic flux enclosed by this loop is changes as the time varies. So we are supposed to have induced EMF, electromotive force, induced EMF, and which will produce a current in this loop. And as you can see here, this loop is, the direction of the loop is marked as clockwise in this way. Okay, so the direction of this loop is in which direction? So use your right hand, follow the direction marked on the curve on the plot. So the direction of the loop is pointing toward the positive z direction. All right. So here is the background information about the problem. So we know that the movable bar, the red one, is moving from left to right at a speed of v sub 0, and the background magnetic flux density is uniform and is in the z direction. So it's returned as b sub 0 in the az direction. And we know that as the time increases, the amount of magnetic flux enclosed by this loop is increasing because the loop is getting larger and larger. So using the Faraday's law, we can calculate the electromotive force induced by this scenario. And first, let's calculate the amount of magnetic flux enclosed in this loop. So it's an integration, a surface integration of the magnetic flux density, B. So this equation finds out the amount of magnetic flux enclosed by this loop at a given time. So the surface area can be decomposed into two-line integral. One is from x equals to 0 to L, and the other is from y equal to 0, which is at the left end to the right. And as you can see here, the right end is marked as y sub 0 plus v sub 0 t. Now, because the movable bar is moving as the time changes. So its position is marked as y sub 0, which is the position when t equals to 0, plus v sub 0 t. So as the time t increases, the position will get further to the right. So unfortunately for this integration, the integrand b sub 0 is a constant. So it's simply a product of b sub 0 and the surface area of this rectangular space. So the integration result is B sub 0 times the height L and times the width, which is Y sub 0 plus V sub 0 T, as you can see from this result. So this is the so-called magnetic flux phi enclosed by this area at a given time t, okay, at a given time instant t. However, this is not the end of our calculation. This is only providing information of magnetic flux at a given time. To find out the electromotive force, we need to do the time derivative, as the Faraday's law says. All right, so in this equation, we see this kind of summarize what we have seen in the previous slides. And this integration is relatively simple because the magnetic flux density B happens to be perpendicular to the surface, which is, to put it another way, is that the B sub 0 direction is the same as the normal of the loop surface. So the calculation is relatively simple. All right, so next, as the Faraday's law prescribed, you need to take the negative of the time derivative of magnetic flux enclosed by the loop to find out the electromotive force enclosed on this closed loop. Okay, so EMF, electromotive force, again, is the line integral of electrical field intensity E at a specific path. So what is the physical interpretation of this integration? 注意到这边的 EMF 是什么？电场的线积分啊，所以电场经过路径积分之后，它的物理单位是什么？电压嘛。好，所以 EMF 这个东西它等同于电压啊，等同于电压。所以意思就是说，绕这个电流回路一圈所得到的电压，它可能是一个正值，也可能是一个负值，但它不等于零的条件是什么？不等于零的前提是什么？不等于零的前提是等号右边这一个磁通量的时间微分不等于零嘛？好，所以只要这个电通量的时间微分不等于零，那这样绕一圈下来，它的电压就不等于零。那假如它不等于零的话，这一个场就叫做什么场？保守场还是非保守场？非保守场。OK， 谢谢。2个礼拜不见，大家还对我有反应啊 ？OK， 好，感谢啊。所以 ，all right， we need to take the time derivative of the magnetic flux calculated in the previous slide, and as you can see here, because we are taking the time derivative, so the whole expression here, we have two terms. And the first term is a constant, which is invariant of time, while the second term has a time dependence. So the time derivative is relatively simple. It becomes B sub 0 L times V sub 0. Okay, so I guess you have no problem with that. And remember to take the negative. So the negative only implies that the voltage, the electrical field is pointing to which direction. So take a look at this figure again. If the EMF is a positive value, then the current should follow the direction of the of the current loop direction marks, similar to the direction as it marks. So if the value is a positive one, then the current flow should be clockwise. And in this case, we happen to have a negative value, which means the voltage is higher at the lower end and smaller in the top end. So the current flow is counterclockwise as marked in this plot. Okay, so this EMF, this electromotive force, will drive a current, a counterclockwise flowing current in this current loop, as the bar is moving from left to right, because there are more and more area enclosed by this loop. There are more and more magnetic flux enclosed by this loop. So to put it another way, as the bar moves to the right, there are more and more crosses. There are more and crosses enclosed in this loop. So as the Lenz law says, what is the induced current do? What happens with the induced current according to the Lenz law? It works against the change. So in this case, we see there are more and more crosses. So the Lenz law tells us the induced current shall produce more dots to cancel out the crosses, increase as the time changes. So let's see what this current produce. If the current is flowing up, it's going up, what it produce in this area? Use your right hand, it produces dots. It produces dots. On the other hand, if the current is flowing down, it will produce more crosses. Okay, so intuitively, use your right hand and use the Lenz law, you can guess that the induced current should flows up so that it produces dots to cancel out the increased amount of crosses. Okay? So use this principle to check up your result. All right? 所以在解题的时候，当你算出来你的感应电流的方向，或者是你的电压的方向，你试着用冷次定律去校对一下，你的答案是否合理啊？因为你的根据这一个冷次定律的关系，你所产生的这一个感应电压和感应电流，它的那个工作的方式是要去对抗原来的变化啊，所以在这个例子里头，你的叉变多，所以你的感应电流应该要给你点点的磁场来去对抗变多的叉。Okay, and on the bottom half of this slide, it provides an alternative interpretation about this problem. The induced EMF can also be interpreted as being due to the electrical field induced in the moving bar by virtue of its motion perpendicular to the magnetic field. In our previous discussion about the Helmholtz force, we know that the magnetic force can be expressed as the L cross B I dl cross B. So the magnetic force can be interpreted in terms of current flow, but it can also be interpreted as QV cross B. So this current flow. It can be also interpreted in terms of moving charge. So in this case, V is what? V is the speed of moving charge. So for this case, as from our previous derivation, we know that as the bar moves to the right, there is a current flowing counterclockwise to produce dots, to produce magnetic flux that cancel out the increased amount of background magnetic flux. And to think of the currents that flows up, you can interpret it, you can think of it as electrical charges moving up. So the velocity of the charges are moving upward. And so that will be V goes to the, oops. Oh, I'm sorry. The charge are reside within the bar. 这些电荷是在这个金属棒上，它被拖着往右边走，所以对于这些电荷来讲，它原生的原来的这个移动速度是往右边的，所以这边写作 V0AY， V0AY。而背景磁场是在叉叉方向，也就是 Z 方向，所以 V0AY cross V0AZ 呢是一个往 AX 方向的力所以对于电子来讲，它感受到的作用力把它往上拉、往上推所以往上推的电荷就形成了这边所看到的逆时针方向旋转的电流。OK， 所以这边要留意一下这边指的 V0 是金属杆往右边移动的那个速度。OK， Alright, so the true interpretation will provide the same result. Okay. So to an observer moving with the bars, its force appears to be an electric force due to the electrical field, F. So in this case, or for the moving charge, you can think of the force equals to Q times E, the electrical field intensity times the amount of charge. So if you balance the two equations, you will find the electrical field, E, equals to V sub 0 times B sub 0. So the electrical field intensity is proportional to the product of the moving speed of the bar and the magnitude of background magnetic flux density. All right? And if you do a line integral of the electrical field, if you do a line integral of the electrical field, from 0 to L in the x direction, then using this result, you end up with B sub 0, B, L. I'm sorry. Now it's a little awkward. Okay? So you end up with this result. So not that the voltage difference only appears on between the bottom and the top of this bar. Okay? 所以比较小心的就是你把刚刚那个式子做线积分之后那事实上也就是说这边的电流驱动是来自于这一根移动的金属 条上面上下位置的电位差，上下位置的电位差，而这个电位差的大小就会是 V0B0 乘上 L， 因为你的电场强度是 V0B0， 而你的那个有电场的那个区段呢是 L 的长度，所以乘起来之后是 V0B0L， 所以这个是你的线段上面的电压差 ，OK。And because of the presence of this voltage difference, you will produce a counterclockwise current, produce a current in the counterclockwise direction. And this concept of induced EMF is known as the notional EMF concept, which is employed widely in electromagnetics. So the implication of this example is that if you keep moving to the right on this environment, you will produce more and more electrical energy because the mechanical energy that you exerted on this environment. 所以在这个环境底下，因为你的机械力的做工，而这些机械能呢，就可以被转换成电能，所以这也就是发电的基本概念，那当然，这一个发电的方式看起来就有点蠢嘛，OK， 因为你要走一个很长的那个的轨道，那所以当然你学过那个发电机的这一个基本架构嘛，所以我们通常都是以旋转 rotation 的方式来进行发电。我们等一下会讲到一些 case，OK？ Alright, so in the two examples that we have just discussed, we have implicitly illustrated the principle of the two-particle application of a Faraday law. One is the reception of radio and TV signal using a loop antenna. And the other is the electromechanical energy conversion, as we have just illustrated in the previous example. And the key point is the loop. First is you need to form a current loop, so that you can effectively intercept the magnetic flux, so that you can produce the electromotive force, the voltage difference to produce currents. And so the loop, the one key is the loop orientation. So as we have discussed before, that the loop orientation must be will works more effectively if the loop orientation is the same as the magnetic flux direction. On the other hand, if the loop direction is not parallel to the magnetic flux direction, then it will work less effectively and produce only part of the only part of the magnetic flux. Okay, and in this case, in this figure, originally it's illustrate the magnetic flux generated by a current. So as you can see, if the current goes this way, and using the right-hand rule, you will produce the magnetic flux directing from left to right. However, if you rotate the current loop by 180 degrees, then the current will go in an opposite direction in this figure. Then the induced voltage, the induced magnetic flux will change its direction as well. Okay, so the orientation of the current loop matters, as you can see from this illustration. And here are a few examples of loop antenna. As I already told you before, for AM radios, because the wavelength of AM frequency is about 300 meters. So instead of using the so-called monopole antenna, which amounts to at least a quarter wavelength of the frequency, you use long wires, forming loops, to do reception of radio signal. So let's do a little some practice. So if you have a radio station which comes with an antenna mounted on a tower, so here is the antenna, AM radio antenna mounted on a tower. And the current I on the antenna tower is going up and down. It's erratic vertically. So what is the magnetic field produced by this radio tower, radio antenna? Well, use your right hand, right? So the magnetic field produced by the currents can be crosses or dots as the signal goes out of the radio tower. So this is the direction of propagation, similar to you throwing a stone in the water or in the lake. Then you will produce some ripples, and the ripples will propagate outward, pretty similar to what electromagnetic waves propagate. So as the wave goes out, the magnetic field will go this way and this way. Why? Because the current's going up and down. So use your right hand to imagine that the magnetic field will go to this direction, and in the next moment it will go to the opposite direction. All right. To receive, to feel the electromagnetic wave, we can use a loop antenna. Which is essentially the device shown in the figure. So how should you orient your loop antenna? 你的天线的那个摆向应该怎么摆？要这样摆呢，还是这样摆？假如说这是一个 loop 的话，你的摆向的目标是怎么样？要拦截到够多的磁通量嘛，所以假如你这样摆的话，你会不会拦截到那个磁通量？不会嘛，所以你要这样摆才会拦截到磁通量。所以伫古早的时阵那个听收音机的时阵那个天线拢爱甲翘起来， 敲一个手，敲一个，因为拄啊好会当收到这个讯号。我们当然现在的小朋友当然没有这种经验了哈。OK. Alright, so as you can see from the plot, you should orient your loop antenna in this way so that it will intercept the maximum amount of magnetic flux due to the direction of the radio signal. And so we can understand that the loop antenna orientation should be adjusted to improve the reception performance. And we also know that the amount of EMF, the induced EMF, electromotive force, is proportional to the loop antenna area. So AB is the loop antenna area. Well, so it's a square loop. The amount of is proportional to the magnetic flux density B sub 0, and it's also proportional to the frequency of the signal. So higher the frequency, the larger the angular frequency over here, omega. Now, omega is the angular frequency, which equals to what? Equals to omega equals to 2 pi f. So it's referred to as the angular frequency, 角频率, times sine omega t, which is the time derivative of cosine omega t. So if we suppose the original signal is cosine omega t, in the form of cosine omega t, it becomes omega sine omega t, as you can see in this equation. Next, and here's an interesting story. All right, so we know that the loop should orient it that way so that it can maximize the amount of signal. And in this case, it's an interesting story for locating the source, the radio source direction. All right, so next is the example of electromechanical energy conversion, which means 发电嘛，发电, all right? So as we see in example 2.4, you can use this configuration to provide electromotive force. Note that in this case, there's a magnetic force pointing to the left because of the induced current. Because the bar is moving to the right, so you have a more electromagnetic flux enclosed by this loop. The EMF is a negative value, and which produce a currents flowing counterclockwise. And the currents in this environment, in this background environment, will produce a magnetic force using the Biot-Savart law. Based on the Biot-Savart law, this magnetic force is pointing to the left. So which means if you want to move the bar to the right, you need to provide some work. You need to provide some work to work against the magnetic force. So you need to do some work so that you can convert the mechanical energy into electrical energy. So the induced current, the magnetic force experienced by the induced current is the work that you need to work against. All right? And so, of course, this linear movement can provide energy conversion from mechanical energy into electrical energy. However, you already know that this scenario is kind of awkward because you can, it's difficult to maintain a linear movement in this environment. So for practical electric generator, they are mostly in the so-called rotating type. So you have an electrical current loop of limited size and rotates in an environment with background magnetic field. So as the loop rotates, the amount of magnetic flux enclosed by the loop changes as the time varies. So as you can see from this figure, so in this illustration, we have background magnetic field goes from top to the left from top to bottom. So in the positive X direction, and you have a current loop rotating in this way, rotating in the Z direction along the Z-axis. So the amount of magnetic flux, the time derivative of magnetic flux enclosed by this loop can be found as omega b sub 0 A, which is the area of the loop, times sine omega t, which originated from cosine omega t of the signal source. And so we see that at a different time instant, the electromotive force, EMF, the voltage produced by the appear on the loop, also changes as the time varies. So this is the EMF, the voltage produced in this scenario, and you can see it's also a sinusoidal signal. So the voltage is alternating between positive and negative value. Okay, and the voltage is proportional to the background magnetic force, to the size of the area, and the frequency of rotation. So to increase the amount of voltage, you can try either increase the frequency, the background magnetic field, or the area of the loop. So here is a more practical illustration of rotating type generator. And to one surprise that in this case, or in most cases, the generator, the loop is placed on the outside, while the magnetic field is produced by the rotator, which is also an electric magnet. So as you can see from here, for most generators, a stationary member or the stator carries the coil in which the voltage is induced, and the rotating member, the one in the middle, is the one to provide magnetic field, which is generated. The magnetic field is also provided by electricity. But as long as there are no electricity produced by the generator, then the electricity provided to maintain the magnet, then this is a cost-effective one. 所以一般来讲，那个发电机里头的那个磁铁也不是固定磁铁啦，所以这边你可以看到那个它的那个磁场是由电磁铁所提供的哈。但是反正只要你输出的能量比输出的电能比你输入的电能来得多就 OK 了哈。但你另外要提供的是机械能啊，所以看是你要用水冲呢，还是要烧煤产生水蒸气啊，反正你要有一个还是弄一个核子反应堆来去烧水蒸气之类的反正你要有一些机械能够让它转起来这样它就可以发电。Okay, and next is an example of of the application of Faraday laws, which is magnetic levitation. So that's a pretty interesting one. The magnetic levitation 磁浮 arises from a combination of Faraday's law and Ampere force law. And we can see that a current carrying coil can be lifted up above a metal plate. And to demonstrate that, let's begin with some simpler arrangement. And in the textbook, it provides an example of making this kind of device using some specified material. So if you have a pair of coils made of 30 to 50 turns of number 26 wire of about 4 inch in diameter. 它这个写法其实对美国学生来讲还蛮简单的就是说你去五金行买26号的线，然后绕个30圈大概以10公分为直径的圈圈绕个30圈就可以做得出来那他这样写的原因其实还是为了安全就是说你希望能够达到这个效果，但是又不要让它过热那个线圈可以是7包线或什么之类的OK。然后呢，你必须要把这个线圈接上所谓的 variac， 这边 variac， 这个 variac 其实是一个什么？可变的交流电源所以我那个时候在备课的时候去查一下 variac 的图片就找到这个图片，结果它下面标的是 National Taiwan University of Science and Technology 所以我们台科大的那个电力组还是蛮牛逼的OK 所以我查那个 variac 这种古老的元件这只有台科大有 OK Alright, so as you can see from this plot, so you have a fixed power source which is 110 volts alternate AC source. And using the variac by dialing by tuning this dial, you can control the amount of voltage provided with this AC source. Okay, so you want to gradually increase or decrease the power provided to the coil, because once you connect the coil to the variac, you will provide currents with actually relatively large currents in the loops. Okay, so the first case is connecting the two coils in the same direction. So the current flow in the two loops are of the same direction. So what happens? What happens with the two coils? Try yourself. 对啊，相吸还是相斥 ？Okay, all right. So suppose that we have a current going up in this way, a current loops going up. Then it produces magnetic flux in this direction as dot labeled over here. And because the other loop also carry a current, then you can use which equation? I dl cross B to find out the magnetic force act on this loop. So L cross B, it ends up in this way. So the force is pointing to the right for this loop. And for this loop, because the field produced by the magnetic field produced by this loop is in this direction. So again, L cross B, okay, so it's pointing to the left. So the two coils, the two loops of the same current direction will attract because the magnetic force of the two are of opposite direction. So they attract to each other because of the same current direction. On the other hand, if the two coils, the currents flowing in the two coils are of opposite direction, it will produce some repulsive forces. Okay, so loops of opposite current direction repulse to each other, right? So the first case, if the two currents are of the same direction, they will attract. The second case, if they are of opposite direction, they will repel. If the current, okay, so this is what we have here. Next. Okay, so connect coil number 2 to the variac and coil number 1 to an oscilloscope and to observe the induced voltage in coil number 1 to demonstrate the Faraday's law. So by adjusting the voltage in the variac, see what is the direction of flow. Okay, so this is, so for this case, before proceed for this case, let's try another case, okay? So here's one case that connects to the variac. So suppose we have this current. And if you have the other loop as our open circuit, what happens to this loop? Well, nothing. Why? Because it's an open loop. So you cannot form a complete current flow. So if the second loop is open circuit, then you observe nothing. All right? What happens if the second loop is correct? Let me put it in. 这样画好了，这样画比较好。对。Okay. What happens if the second loop is a short circuit one? Is a closed loop? Well, let's see. So if the current is flowing this way, then what is the magnetic field produced by this arrangement? So use your right hand. Okay. So for a specific time instant, if the current is flowing this way, it will produce magnetic field in this direction. As the current is getting bigger and bigger, there will be more and more magnetic flux going to this way. So what is the induced current in this loop? 在第二个短路线封闭回路当中，它的感应电流应该是这个方向呢，还是反过来？我们要用什么原则来去判断？冷次定律嘛，哈。所以，假如说这边的电流越来越大，也就是这边的箭头越来越多，那表示什么？我要产生一个电流来去对抗这个箭头，所以它应该你的感应电流应该是这个方向呢，还是反过来？反过来嘛，哈，反过来才会给它反过来的箭头，好，所以感应电流的方向跟原生的电流是同方向还是反方向？反方向 ，OK。那既然反方向的话，它们是相吸还是相斥？等一下，我们前面的第一个 case 是同方向的是相吸哦，反方向是相斥。所以，假如说你现在是一个有电流，另外一个是感应，那它因为什么反向的电流，所以它们应该怎么样？相斥嘛，哈，相斥 ，OK。 好，所以自己要测试一下哦，自己要测试一下。以这个 case 来讲的话，它是2号有接电源，1号是感应啦，它是说接示波器啦，其实就跟短路是一样的。好，它1号是单纯的那个感应电流，所以从那边的判断，我们可以看到，根据冷次定律的话，你的1号线圈中的感应电流跟2号线圈的那个电流应该是反向的，因为是反向的，根据冷次定律，所以它们会造成一个相斥的力，因为方向相反。Right， 所以 for this case, as already mentioned, if you have an open loop, then you will experience no induced currents in the loop because it cannot form a loop currents in an open loop. So it won't get affected because it has no induced current. And if the other loop is the closed loop, then it will have some induced current. And here's an example of 窃听器啊 ，OK， 但对啊，这是窃听装置啊。当然，这个东西当然现在已经不太适用了哈，因为没有人在打那个 landline 了哈。啊？我曾经觉得我的电话有被偷听过。没有，我觉得有。但有的时候不是故意的啦，有的时候你那个线摆在一起靠得近哦，它其实我们叫做什么 crosstalk。So if you have two current loops placed next to each other, it's possible that you will be interfered by currents on other current loops. It's referred to as electromagnetic interference, EMI. So in the industry, the so-called EMI and EMC, electromagnetic interference and electromagnetic compatibility issue are relatively critical for the design of electronic devices. 因为我今天超时间好多哦 ，OK， 好。我先讲完这个好了哈。So as you can see here, because as I already mentioned, that for the landline, the signal is actually unmodulated. So it's the baseband signal, which is pretty much the acoustic wave transformed into electrical one. So because there is no modulation, so as long as you can capture the magnetic field produced in the original current loop, then you can get the information, the acoustic wave signal from the second loop. So conventionally, 或者是说正规的话，那个电话线的讯号应该是2条线呐，排在一起，这种我们叫做 differential signaling， 差分线路了哈，差分线路 differential signaling， 也就是说，在这个电话线，在这个线路上面，其实不仅仅是电话线，你现在所有看到的那个 PCB 板上的那个电路。基本上讯号线都是 differential signaling， 也就是说线段其实是讯号其实是一去一回的，一去一回的。那电话线也是这一种，但假如你要窃听这种电话的这种 landline 的这个讯号的话，那你事实上就是把电话线的那个2条扯开来，变成像这样子。这样子的话呢，你就有一个一去一回的 current loop。那这个一去一回的 current loop 就会给你什么？对不对？点点 ，OK， 右手定着嘛，那就会给你点点的磁场。当然，只要电流讯号反过来的话，就变叉叉了嘛，那这个时候呢，你再把你的窃听用的电话。窃听用的那个讯号 回路摆在这中间，让这一个讯号，让你的那个窃听的那个回路能够去拦截到这边的叉叉或者是点点。那根据冷次定律，它也会感应到电流。虽然说这个电流的方向跟你原来电流方向是相反的，但是对于声音讯号来讲，那个方向是没有差的嘛，它的是特定频率的变动，所以传统 landline 的那个窃听技术还蛮原始的啦，非常简单的一个机制就可以完成。好，我们先休息一下，休息5分钟。